So today I'll be discussing some work that was published in the eLife Journal in January, titled Emergent Trading Behavior in Multi-Agent Reinforcement Learning. This is work done underneath my advisor, Jordan Pollock, at Brandeis University. There's usually stuff at the bottom. Can I make the toolbar disappear? Okay, we'll just deal with that. Okay, so we're going to start off this talk a little bit interactively. So who here is heard of Minecraft? Raise your hand. Most people, and if you're not raising your hand, you're probably lying. All right, keep your hands up. Who here has played Minecraft? All right, I can't do the mic and I hold my hand up, but keep your hands up if you have played multiplayer Minecraft. Okay, less hands now. Okay. Who here has ever traded resources with another player by dropping items in the game that the other player picks up and vice versa? Raise your hand. Okay, a good amount of people. You guys know what I'm talking about anyway. So basically, we're kind of doing that in this work. I wanted to make AI do that, and so we did. And so the motivation for this work was basically that I played Minecraft when I was in high school. I'm sure some of you did as well. And on multiplayer servers, players would form towns, roads, and whole economies even. And they collaborated to make large-scale, remarkable projects that like no one could really do alone. And I was really impressed, and I love that kind of stuff. And so I thought it would be cool to create an artificial society where AI learned to work together to survive. And that was kind of my ambition when I set out to do this project. And this is kind of related to the field of cultural evolution, which is kind of the study of how human culture emerges. And there's been a lot of work that I've kind of read that's been really inspiring. So if you're interested in this, cultural evolution is a great field to read up on. So raise your hand if you've heard of the prisoner's dilemma. Okay, thank God. Okay, so my issue with the prisoner's dilemma is that it assumes cooperate is a simple pre-programmed choice, but that's not the case in the real world. Cooperative relationships can be incredibly complex. The evolution of cooperation by Robert Axelrod in 1984 showed that cooperative relationships can form when certain pre-existing conditions are met, namely that agents must repeatedly identify and interact with other agents in order to form a relationship that's kind of built on trust. And there's kind of a cool example of this where in World War II, soldiers who were in the trenches against another constant opponent, they kept forming informal ceasefires, even though their commanding officers were trying to make them fight because they could identify the other opponent and they were engaging with them over and over again for a long period of time. And so I wanted to create a more complicated form of cooperation, like the Minecraft embodied trading. So I set out to do this, and it was harder than I thought. And so I began to work on this. And so I had an initial grid world environment consisting of two types of food and two agents. And I experimented a lot with the environment. I tried out a lot of different things, but I found that agents really did not like trading. Like they really avoided it. So I experimented with kind of like a closeness reward and a death mechanism, basically, so that agents would really want to be close together and they would die if they didn't have both types of resources. And that seemed to kind of work. But then this came out and I got really scared because I worked like 8 months on this and DeepMind published a paper that was basically what I was trying to do. So I looked at their paper, it's like 100 pages. And their environment uses 19 possible hard-coded trades. And so instead of agents dropping and picking up items, there's just different actions that they can execute for different ratios of trades with agents in a certain radius. And the trades are automatically executed by the environment once both agents accept. And you kind of get this bartering form or bartering behavior that emerges because they'll start off with like a really like bad offer for the other agent and a really greedy offer for themselves. And then they'll kind of get lowered down a little bit until they can kind of agree on something that's fair for both of them. However, this was in the paper. And basically, they said that they tried the drop and the give actions that I was experimenting with, and it appeared moot. It basically was not working. Agents refused to use these actions like I was seeing in my work. I went, oh no, that's not good. If DeepMind can't get this to work, what hope do I have? And so I reached out to the authors, and they're really nice people, by the way. I showed them my current setup with the closeness reward and the death penalty. And they were like, yeah, like your agents are kind of trading a little bit, but they seem to be, or they could be keeping others alive just so that they could be close to them. And the idea was that if you're incentivizing agents to be close to another agent, and you're also giving them rewards for not dying, then an agent will die if you don't keep it alive somehow. And so that was kind of their theory for why agents would trade with each other in my toy setup. And that seemed kind of fair. And so they said that a market mechanism of some kind that doesn't reward agents for keeping each other alive could be helpful. And so basically, this would be a sort of meeting point where agents would go to exchange resources. And they had a similar idea in their paper. Their market automatically executed trades. So the agents wouldn't trade with other agents at the market. The market could just kind of act as an automatic shop. And I thought this was a good idea, some sort of way to get the agents to kind of congregate. But there were a few questions that I had or wanted to answer when I was actually doing this work. So one, how do I even make them go to the market if they're not getting free food while they're at the market? How do I make them go at the same time as another agent? So how do I kind of coordinate that behavior? And how do I make them stay long enough to trade? Because if they go to a market for some sort of, one-shot reward, and they leave, and the other guy comes and he stays there for a little bit, and then he leaves. They miss each other, and they don't get the trade. So, what if we gave the agents time to do absolutely nothing together? And so we implemented a day-night cycle. And so basically, the way that this kind of works is it makes the environment more of a periodic environment where there's a portion of the environment that's daytime and a portion of the environment that's nighttime. And at the nighttime portion, there's a little campfire in the middle that has a little bit of light. And the idea is that you punish the agents for being out at nighttime. And so at nighttime, they kind of get close together and they stay around the campfire, huddled together, unable to forage, and they spend the entire time with absolutely nothing to do, basically. So it would be a very boring game if this was a human game, but luckily these guys are AI agents, and so I don't care if they're bored. So the idea is that they go out during the day, they go to these patches to collect food. There are two types of food. There's fruit and there's greens, indicated by the red and the green tiles on the map. They get reward for collecting the food from the environment, and they also consume the food automatically at every single time step, and they get an extra bonus for consuming both types of food. And so that's why they would want to trade. They go to one patch, they collect the fruit, for example. They have that fruit, they're slowly consuming it, but they also want to consume greens at the same time to meet all their kind of nutritional needs. And of course, they want to stay in the environment. What we do is we punish them for being out at night, basically. So they really learn to quickly avoid being out at the nighttime. So the actions that these guys can do, they can move up, down, left, or right, as is traditional on a grid world environment. They can also do nothing, to just stand in their same cell and not do anything. And then they can also pick up all the fruit on their current cell. They can pick up all the green on their current cell. They can also place half a unit of fruit or half a unit of green on their cell. So if they each had one of each resource, they could drop half of a resource and exchange it. And so I'm not going to spend too long on this slide, but basically agents are able to see the fruits on the map around them in a local area. They're able to see the greens on the map around them in the local area. And they're also able to see the light level in that area too. And in addition, they get to see the position of themselves, and that's a separate observation, and then all the other agents in the map. So there's 4 agents in the setting. And so they get to see themselves and 3 other agents, and they can also view how many resources each agent has at that location. And real quick, we use the proximal policy optimization algorithm, PPO. It's a very straightforward algorithm. I'm not going to spend too long on it, but we use the single agent version of this because that's what the DeepMind authors use for their multi-agent work as well. And it just has a vision network, memory network, dense network to actually choose the actions. So vision, memory, and controller, basically. And so the results is that the agents learn to develop a protocol to exchange around the campfire. And so basically we call this the drop swap protocol. And so what happens is agents will line up with a partner one cell away. They'll drop a resource. They'll walk over to a partner's dropped resource, and then they'll pick up their partner's dropped resource. And so we call this the drop swap protocol. And this occurs in 9 out of 10 trials, and we'll get to that last trial in a second. Basically, what you can see here, is my mouse visible? I don't think, oh, here it is. Is that visible? Yeah. So very quickly, the agents learn to forage, as you can kind of see over here, but they kind of plateau their reward for a little bit. And this is actually like a day of real life training time, by the way. And they kind of just stand at the campfire doing nothing for quite some time. But then eventually they start to learn to trade, as you can kind of see at around 50,000 training iterations in. And they slowly learn to just trade more and more resources and they kind of explore that behavior space. And then they kind of plateau at the maximum amount of resources that they can trade. And so we wanted to know why agents always trade by dropping resources one cell apart. And basically, it would be easier for them to trade if they were both on the same tile. Because, well, can I move this? Cool, okay. Because they just don't have to move. Like this is a form of exchange where they have to move during the exchange, and it would be easier for them to learn the behavior if they just were on the same position. And basically, they hypothesized that they do this to actually prevent someone from taking their resource before they leave it. So they kind of stay on the same space to guard their resource until they know that they can get something else in exchange. And so basically, we wanted to test this. So there are 2 ways that an agent can kind of steal from another agent. They can either just not offer anything in return and grab their food, or they can place an offer, wait for the other guy to place an offer, then take back their offer and try to grab it before the other guy picks it up. And so basically we manually controlled our agents and we interacted with it manually. And we tried both of these settings across all the different possible pairs of agents. And we found that all the agents would kind of pick up their resources if we tried to go over there without offering anything in return. And so they would only drop things if they knew that, and they would only leave it there if they knew that they could get something in return. So that was kind of cool. They kind of like learned a way to defend against being cheated. And yeah, this evidence basically supports that theory. I'm going to skip this slide in the interest of time, but basically some agents learn to trade with others instead of just the same partner over and over again, and some agents can only trade with the same agent, basically. So this behavior doesn't always generalize to all agents. So this is the other trial, mysterious trial. And so basically what you can see here is that the pink drops a resource for the cyan agent before trading with the light blue agent, despite not receiving anything in return. And so we can kind of see this in a second over here. The pink agent will drop a resource over there. The cyan will go to the right and pick it up, and then the pink and blue will go trade. And so as one man once said, this might be the worst trade deal in the history of trade deals, maybe ever. So why would the pink agent possibly give away resources for free to the cyan agent who's not giving anything in return? And so basically, there are some hypotheses for food sharing amongst non-humans. We're going to focus on the tolerated theft hypothesis, which says that people will give other people food or resources because they will fight you or cause problems if you don't give it to them. And so that's what we thought was going on over here. But remember, there's no combat in this actual simulation. So how on earth could the cyan agent possibly coerce the other agents to giving up food? And so we took control of the pink agent and manually stopped it from giving away that resource at that time step. And what we kind of noticed is that the cyan agent will kind of position itself to intercept food between the pink agent and the light blue agent, kind of like a defender in basketball almost, and try to intercept the resources during this exchange. And so what the pink agent is actually doing is it's actually dropping resources away from the trading site that it uses with the blue agent to bait the cyan agent away. That way it can trade in peace and have the cyan agent not bother it while it's trading. And I thought this was really, really cool. It's a way of kind of defection without actually having this kind of program of method of defection in the environment. And so over here, you can kind of see this more clearly. You can kind of see the pink agent drops the food over there, and then the cyan agent will go away, and the pink agent will go to the top and trade with the light blue agent. And so we also wanted to look into how important extended congregation actually was. And so what we did is we experimented with some control conditions where we lowered the light penalty. So P equals 0 means that the agents can basically ignore the light, and P equals 3 means that agents get penalized a lot less than in the P equals 10 setting, which is our control. And so with lower penalties, agents will basically just stay out at nighttime to keep foraging. And they'll achieve less reward with this way than if they just traded, because especially in the P equals 3 case, they're still getting a little bit of a penalty, but they'll still take the penalty in order to go and collect resources on their own. And they refuse to learn to trade basically because the trading is that much harder to actually learn. And so they get stuck in this kind of local minima. All right, so just to recap, emergent exchange emerges between agents when they are incentivized to congregate for a while. The drop swap protocol prevents agents from getting cheated, and agents can still get cheated by non-partners. I didn't cover that due to time, but agents who can't learn to trade also learn to intercept the trades of other agents. And the traders respond to this by baiting them away, basically, so that they can trade in peace, which is a lot of cool stuff that emerges just from picking up and putting down resources. So thanks. Here's a link to the journal paper. Feel free to reach out if you have any questions or if you want to play Minecraft.